Thank you, everyone, for attending my talk. Also, I want to kind of apologize because it's not quite high science, so there will be lots of bit twiddling and assembly. So I'm kind of embarrassed. But on the other hand, I also feel it's kind of important because it really impacts language design and how we program. So hopefully I can get that across. So the talk I'm talking about is what about the integer numbers? And it's really inspired by a title from a beautiful paper by Colin Runcheman, What About the Natural Numbers? And that is very elegant and high science work. So I encourage anyone to look at it. And what he was asking in that paper was already in '89, he was like, why can't we program with natural numbers really well? Because that's a type we use all the time as computer science programmers. And I'm kind of also asking this question, like nowadays, why can't I program really well with real integer numbers like Z, right? So in many programming languages lack really deep support for this. It's not the default, right? We always get by default kind of 32 bits or 64 bits or 63-bit numbers. But I would love to have like real integer numbers, right? Especially because even the most basic laws don't hold for these fixed bit integers. And I would love to like always program like here in a beautiful language called Coca, where the int would default to like big integers, right? And many languages actually do this, right? Like Python and Camel makes it really easy with Z-arith package and Haskell with integer, etc. But it's not like usually the default mode. And why is that really? Well, because it's slow, right? And that's really the real reason. Otherwise, why would you even bother with these fixed bit integers, right? And I find it especially infuriating because you get all these funky instructions for niche domains like cryptography or graphics. Who cares about this, right? I want fast integers. I don't want swizzles. I want fast integer arithmetic. So what I'm going to do here, it's actually a negative talk. I don't have a great solution, but I have some improvements, right? But it's still not great. So I'm going to kind of end with, please Intel ND make new instructions. But I do show some improvements. And it's kind of fun to see how you can improve things a bit. So before I start, I first want to show how we currently do it. Like how Z-arith or integers in Haskell or in Python, like how do people make it like faster? And what they usually do is like you have some kind of fast path for little small integers, fixed bit integers. And then as soon as the arguments for your operations become too big, maybe you're gonna overflow, then you seamlessly switch to pointers. And you have some way to distinguish those. And then you can like seamlessly use big integer arithmetic. But most of the time you'll be pretty fast because you have these small integers that are fixed bit. And that's what Coca uses, for example. And this is why I got working on this. And I'm going to focus in this talk on addition because addition is really cheap on a modern processor, basically free. So any overhead you get is pretty severe. And that's why generally the default is still not real integers. So if you look at, for example, how most systems do it, including Camel, for example, is you say, I'm going to put a little tag bit. The lowest bit is going to be my tag. And then small integers get a 1 there. So I'm going to encode a small integer n as 2n plus 1. And then I'm really going to check when I do additions if both arguments were actually had a low bit set. And if one of them didn't, I'm going to go to a generic slow path, right? Because maybe I'm trying to add 2 pointers to big integers together, and I have to do much more work. But this is all about the fast path, right? And then I also want to check for overflow, if my addition overflows. And if that's the case, I'm also going to use the slow path, right? And then usually I have to fix up the bits when I did my addition. And this is how most libraries work, or at least as far as I've been seeing when I looked around. And you get kind of assembly code like this. Don't be too afraid. It's ARM64. It's more like the general idea is important. And you can actually see that this is pretty tight code. This would maybe be generated by a compiler directly, right? I write it here in C to make it more clear, but you could kind of generate that. And you see there's a test if a bit is 0, like the 0th bit is 0. This is like checking if both arguments are small. Here we see like an addition that sets flags. And then we branch on overflow to both cases to the gen add, right? They would call the generic addition that's the slow path. And this is what Coca had at first. And it wasn't, I was really looking, can I make this faster? Because it's kind of not great. For every addition, you have 5 instructions and 2 branches. And modern processors really don't like branches. So how can we do that better? Because if you implement now, most arithmetic things, it's going to have high overhead. So I'm going to show 3 ways to make this a bit better. And in particular, can we get rid of a branch, right? That would be great. So I showed 3 techniques, and I have cool names for them. Because nowadays, I do marketing really well. So litbit, sofa, and Reno. And I think they're all new, but I can imagine someone did this already, like in the 70s in some compiler. So if anyone knows something, please let me know after the talk. So the first one, like we can do a little bit better because we had this like and at first to kind of check for both arguments for the bits. So we add like a 2-bit tag, but just 0, 0 for pointers. So we align them on 4 bytes, or 0, 1 for small integers. Then when I would add 2 small integers together, I get a real nice effect. So if I add these things together, then only if it's like small and small, the second bit 1 will be set, right? So that's really nice. If one of the arguments happens to be a pointer to a big integer, it won't be set. So now I can test after I do the addition without doing the end operation to see if it was actually correct or not. So now the test becomes like if there was an overflow or if bit 1 is not set, I have to go in the slow path. So now our instructions are a little bit better than before. 4 instructions, but still 2 branches, right? There's like 1 for the overflow, 1 for the word to argument small. So maybe it's even possible to do this with 1 test, like both overflow and we're both small in the beginning. Think a little bit, maybe you think of it already. Or I'm going to spoil it for you. So here it is. So you can encode it like this. This is kind of an old trick too. So now I'm going to encode numbers again with these 2-bit tag in the bottom, like litbit, and then still the numbers are 4n plus 1. But I limit them to 32 bits, and I sign extend up to the rest, right? And now I can do portable overflow detection. I don't need these funny built-in add overflow. I can just add 2 numbers, and then I can look if the result, if I would sign extend the bottom 32 bits, if it's actually equal to the result I got. And then I know that the addition, like on the 32 bits, didn't overflow. This is a very portable trick to do overflow detection, but you do half-word additions. And now you can combine that with that earlier check, where only if 2 small ints are added, the bottom tags would end up to be like 1, 0. And you can do this at once, right? So it's kind of really cool. So if you can kind of sign extend the bottom 32 bits of the result and then compare to like Z or 2. And I have only 1 branch that tests for both. But you do get the OR operation there. So this is called the SOFA technique, sign extended overflow arithmetic. And this is what Coca currently uses. So if you look the kind of operations you get, it looks like this. So you see like in ARM64, you have actually a really nice compare instruction that does this sign extension. And then there's only a single branch left. And that's generally good because we have to think about it. It's still for every addition, right? So it's better, I would say, still still not great, right? But maybe the best we can do. Actually, so I showed this to my nephew, and he said, you know what? I think I have an even better way of doing this. So here he is. It's Renzo. So the Reno technique is maybe related to that. And don't worry, he's 19, but in the Netherlands you can drink beer at that age. So it's like I didn't buy him off with it. So he kind of came up with this idea. Again, we use like half-word sign extended numbers, but no bottom tags. But in the pointers, I will use the top 3 bits, and I set it. I kind of add 2 to the 62. And then it turns out that you kind of get the ranges in the 64-bit space where there's like the small integers between there are 32-bit, and there's a pointer range starting after 2 to the 62th. I don't know, 62nd. And there's a pointer range. And now when you do addition, if you add to a pointer or add 2 pointers together, you will just never get in the small integer range. And you also know that if you do a 64-bit addition on the small integers, only if they overflow, they will get out of this range. So now the comparison is just checking for the sign extension. It's very interesting, actually. So this tests both, right? If both arguments were small and not pointers to big integers, and it checks for the overflow in one test. So now you get I don't think you can do any better at current hardware than this instruction sequence where there's just addition, the sign extended comparison, and then a branch, right? If it happened to overflow or either argument wasn't small. This is not what Coca is using at the moment, but we do have an implementation of this. And now I kind of come to the negative part of the talk, that the benchmarks, which are very dubious. So let's look at it. So here we see ARM64 and x64, the Intel. So I'm going to look at this one, and then the first bars are for the addition. In the paper that I also look at subtraction, multiplication, etc. And you know what? All our hard work was for nothing. If you look at the results, we see first the blue bar is just in32 addition. It's very fast, 0.66 compared to SOFA. Then we have the normal technique that everyone uses. Then we have the lit bit is in brown, and then SOFA is the dark red one. That's the one that Cocax are using. That's the one I concentrate on. Then skip the light red, and then the green is the Reno technique, and that actually seems a little bit better. But this is in a tiny loop where I just do additions. And current hardware is really good at speculating and throwing all its silicon on computing in parallel. So that's, I think, why they're all kind of equal. But as soon as we do more, a more interesting benchmark, we see different results. And I still don't think any conclusive results. So here, the Coca compiler can actually be parameterized by all these different implementations. So I could write little Coca programs for aim queens, Hammings, Pythagorean triples, Takeuchi, like integer intensive benchmarks that don't allocate. And then measure, right, with Clang or GCC, how well they do. So I'm just going to look here at some highlights, right? So the Pythagorean triples are interesting. You see more difference. You do see here that the bars don't look too much difference, but it is a real difference in practice, right? So it's the SOFA technique, the dark red, that's everything's normalized against it, is 12% faster than the other techniques, for example, right? And a little bit faster than Reno. So the small difference make a matter. And then you see the light bars are for GCC versus Clang. So you also see that tiny instruction selection differences also make a big difference. So it's hard to draw conclusive results. I feel that SOFA is most performant overall, closely followed by the Reno technique. So yeah, that's where we're at. I think I have little time left, right? In the paper, I say, well, we could actually really use instructions to help out with this. And I kind of propose the SOFA technique encoding. And I say, it'd be great if I have an instruction that would go fast and just have one branch on overflow flag. And it turns out, and I'm not going to go into it now because I think I have too little time, but it turns out it works really well with non-boxing with doubles, as is done in JavaScript and in some Python implementations. And then that instruction would actually directly apply, even if they're double encoded or pointers to big integers. And you could most of the time, get the fast path with that particular instruction if you encode it nicely, right? So I think it wouldn't just apply to the beautiful ML family of languages, but also more practical scenarios. So thank you so much for listening, and I hope you enjoyed.